started. And go ahead,
Okay.
Riyasat.
Today's paper is SNP. It's a single shot network pruning based on connection sensitivity. So the work they did here is mainly about pruning neural networks and having neural networks that are smaller in size, compressed, and which are still able to generalize uh, well, or at least like get the same performance for the architectures similar to the reference models. Uh, the main motivation for pruning neural networks is like the idea that deep neural networks are like highly overly parameterized, so they are computationally expensive to train and have extensive memory requirements, and spatially these are um, more problematic, especially in the case of real-time applications such as in edge devices and of that sorts. So compressed neural networks utilize model capacity efficiently, and their interpretation can also be like used to derive better generalization bounds for networks. So the main goal of pruning a neural network is to, like, when we have a large reference model, we want to learn a smaller subnetwork of weights from that model that uh, possibly still performs the same. So there are a lot of criterions uh, to achieve that goal, to to prune the weights of the neural networks. So some are based on saliency, such as these papers by Han and LeCun. I think I couldn't go through all the papers. I only have some tangential experience with Han's paper, and I think it's just basically prunes weights that are high in magnitudes. So just very straightforward. And the second way is to like utilize sparsity enforcing penalties or regularizers. There are a lot of those. I think the most common is the L1 regularization, and there are like a bunch of varieties on those. And there's also a recent paper depart that uses a ratio of L1 and L2 norm that also performs pretty good. And I think our work is also kind of based on the uh, uh, ratio of L1 and L2 norms. So a lot of these previous works, a major problem for them is they have uh, really expensive prune and retrain cycles. So what that means is that it's kind of heuristic, and you have to prune the network, train the network again, maybe prune again, train again to like achieve very good model performance. And there are usually a lot of hyperparameters involved that also needs to be tuned in those cases. So what SNP does tries to do is like uh, they want to prune the neural networks in a single shot at the time of initialization. So to that end, SNP introduces a saliency criterion that identifies connections in the network that are uh, important in some way, and keeping those connections would result in a much more compressed model that still generalizes well and also performs uh, as well as the reference dense model, at least on the training data that we usually test our models on. So SNP finds these important connections based on their influence on the loss function, at a variance scaling initializations, which they call connection sensitivity. So their problem is like given a desired sparsity level, redundant connections are pruned once prior to the training, and after pruning, they just uh, fix those weights that they consider important and train those weights, holding or fixing the other weights that have been pruned during the training phase. So the neural network optimization problem can be.
Can I ask something?
Yeah, sure.
So you said that they freeze the weights. Does that mean that the model cannot be compressed? Because that means if you put them to 0, you can compress them away from the model and you can have a compressed version of the model. But if you keep them 32-bit integers, you'll still use the same amount of space, right? Or do you put them to 0? That's my question.
Yeah.
When
yeah.
They freeze the weights at 0, right?
Yeah.
Okay, so they don't freeze like the random initialization. That's what I thought maybe
Right.
happened.
Yeah. Like when
They just mean the 0 weights don't train.
Yeah. Like during back propagation, you just change the gradients to 0.
Yes, but do you also change the weights to 0? Because that reduces the memory usage and like computation.
Yeah, you also change the weights to 0 as well.
Not necessarily. If you're using, if your implementation is specifically sparse matrix multiplication and it's done efficiently, then it reduces the memory. But if it is, if you just put a mask.
I mean, I'm talking about a good implementation. Obviously, if you have like a good multiply and accumulate GPU that handles like a local sparsity very well, then you will have like a huge memory reduction in computation.
Yeah, I think that's the goal of all these pruning papers. But I mean, most of them don't usually go to that length while they're testing, because there are, I think, algorithms that can take care of that. I think the paper here, Han et al., I think they also use, sorry, oops, I think I broke the internet. Yeah, so this Han et al. Paper, I think they also use Huffman encoding, so to more capitalize on the sparsity. But yeah, the other papers just like stay in the realm of just keeping those zeros and training, and leave the exploitation of that to other algorithms, I guess. So neural network pruning as an optimization problem. So we can frame the pruning of the neural networks by this optimization problem, where we have a data set D and weights W. So this loss function can be any loss function or the standard cross entropy loss for this case. And the constraint is the L0 norm is upper bounded by some kappa, which is between 0 and 1. So the saliency-based methods treat the above problem as selectively removing redundant parameters. So we need some kind of criterion to identify these parameters that we consider redundant, and finally prune the network. So historically, there have been some popular criteria. So a very popular one was the magnitudes of the weights. So you just simply prune the weights that are very close to 0. So Han et al. Does that, and there are a bunch of papers that does that.
So I feel, Riyasat, I feel we're missing context. I'm sorry. It's like, yeah. I feel you just jumped into the pruning, into SNP. It's like, my immediate question is like, why would we need to prune? Okay, to make something smaller. Why do we need a single shot pruning? What, like, and oh, you're pruning even before training. So why
Yeah.
is all of that, like, is it significant? Is it dumb? Remove the large weight of randomly initialized or small weight of randomly initialized. Like, so like a little bit, I think it's just like going too fast. Even I know, like, you're jumping into a formula, but what a formula is a language. Why is that formula? What are we trying to convey? Like, the first question is, why are we pruning at all? And at which stage? Pruning for training, and that confused Eloy. So we prune first, but then we have to train, right? I can prune after, and then whatever I'm running inference for, like, could be sparsely implemented, densely implemented, depends on the device I'm running it, whatever it's efficient, right? But
I mean,
why do I want to prune before? To make the training efficient, or to make inference efficient, or what? Like,
right.
can you?
Yeah, I think I wasn't necessarily confused by before training, because I think it makes sense. Like, you reduce the computational requirements because you have less multiplications you have to perform. If you implement it well, you have less multiplications in the forward pass, and you have less gradient updates you need to do in the backward pass.
You're thinking about for training, right?
Right, for training. So I mean, if you like, that quickly adds up, right? Because you're doing training normally for something like 15 hours. If you reduce the number of multiplications with, let's say, 40%, and the number of gradient updates with 40%, you can get like a huge, like, training speed up, I guess. Especially if you know that they're not going to be used anyways, like after training. If you know these weights are not going to be used after training either, then it makes sense to just remove them beforehand, so you also speed up your training process. I think I was just more confused with, like, if you freeze your encoder, normally what I would think of is during inference, you freeze all the weights, so they're all still 32-bit integers, but they're not zero. You know, they're still like have a value, and then you do a forward pass. That's what I was confused about, because what I thought was, if you freeze your random initialization and just don't update some of the weights, you're still left with the same, like, time it takes to do a forward pass, for example.
Well, but I think because they are using dense methods, they are the freeze at zero tells me that they are just using matrix multiplication, the regular CUDA stuff, nothing
Right.
like nothing over optimized. But still, usually, like, what you're saying is counterintuitive to what we know about over-parameterized models. That adds another flavor to this work. We know, Belkin et al., all of our experience, that we need large models over-parameterized to get best results in those methods. So, but then historically, we have the model that we want to run on the phone. We don't care about the training. We care about the best result. And in the best result, we solve the problem. Take the largest possible model, lots of data, and you'll get the best result. Now, how can we put the trained model on the phone? And by training this largest possible model, you expel the energy less than it takes you to get from your home to Trend Center and back. You burn, we talk about this a lot, about electricity and stuff, but actually in our cars, we emit more CO2 and all of that. But it doesn't matter. That's an aside. The thing is, okay, we have a trained model, how to put it on the edge device. We developed the thing not covered in this talk called distillation, right? You take a smaller model and you train this model on the larger model predictions, the last layer. You try to match the last layer before the softmax, basically. And then you can run the smaller model on your phone. That's the traditional one. Then all the methods that Riyasat is talking about, all the methods in this paper mentioned as background, they're trying to take slightly different approach. Let's do pruning of the model parameters. But if you only prune, say, 20% of the model parameters, you still, it will be inefficient to use sparse methods, sparse matrix multiplication methods. You still will end up using larger models. So you need to be like, leave only 2% or something like that, like very sparse. But then my question is, and the beauty of this work is, like, how can you, given distillation process, we take a trained model and, you know, remove what's not needed for the task. The model is very good, by removing things, we see, remove something and see if performance degrades. Okay, keep removing such that the performance doesn't degrade. But when we take a randomly initialized model, there is no performance. And still, in this paper, they are able to prune this model without actually any parameters or any information about the final performance, because the model is not trained about, and like those things. That's it. I thought that part was
it's actually funny you mentioned that. They did a paper on randomly initialized models. If you do 100 random initializations, you can sometimes get off of 2% of the best state of the art on ImageNet at that time. This was in like 2018. They just tried like a bunch of different random initializations and then took the best one, and that was almost state of the art. So it was pretty funny. Like, you don't even need to train. They were just like, if you randomly initialize well, you can get like a high performance. It's not the best, but like it comes close to state of the art, which is because it's so over parameterized, right? The randomness sort of induces some like
this is getting very philosophical, but very good for students. Basically, what my conclusion from what Eloy just said is, instead of sitting on your butt and not doing something, you have better chances of winning just by doing something, because randomly you can be successful and become a billionaire, whatever, or a top professor. Just do something.
So, okay. I guess on the same vein, there was one of the paper that fits random labels, and they're like randomly shuffling all the labels and making them wrong and still able to generalize, achieve training and convergence. I guess I'll talk about that at the end of this talk. And they also provide that experiment. It kind of helps to decide whether the model is generalizing well or not. How does like the SNP method is actually implemented, or how does it functions? So usually in the general optimization problems, SNP introduces an auxiliary indicator variable C. So if you have like M model weights, then for all those M model weights, we introduce an indicator variable. So you necessarily like double the network parameters. So for every weight, you have one associated indicator variable. So you can get an idea about how each of these weights, whether they are relevant or not to the training and to the loss function, by deciding if we can switch that weight on or off. So you can then train this is just the Hadamed product. So for the loss in that setting, with a change of the indicator variable from 0 to 1, you can measure whether turning each of these weights, if you turn them on, how does the loss change? So basically this becomes a combinatorial problem, because if there are M weights, then you need M plus 1 passes through the whole forward passes through the model, because you need to switch on and off each of those weights. So that's like making the problem even worse. So, but they kind of like solves that problem by taking the relaxing the constraint on the indicator variable. So you, instead of making a binary 0 or 1 that decides on and off, you can just make it smooth, so that when you take the derivative with respect to the indicator variable of the loss function, so you have it's differentiable. So that way, like if you slightly perturb every weight in the network, every indicator variable in the network, you can then like gauge how the weight changes. So that gives you a like pretty good idea about how what is the effects of each of the weights on the loss function. So this is like not the gradient with respect to the weights. It's the gradient with respect to the indicator variables. So that's how you create the they create the criterion. So they just take the like the magnitude of the gradient of that loss function of that gradient for each of the weight normalized by all of the weights. So the higher the value of that gradient, the more important that weight is to the training of the network. And how they do is like they pass one mini batch of data. So this is dependent on like the initialization of the network and also the data of the network. So this is like reflected by this equation is like dependent on W and D. So you pass one mini batch of data through the network and then take the derivative with respect to the indicator variables. So is there like questions or still confusing about something? Or should I? Okay.
Yeah, it seems that they don't actually define the indicator function. At least I couldn't see anything in the paper. Did you have any insight?
Yeah. So here, like the initial loss function is just like minimize the loss function, the general neural network loss function. So what it is like here the C is the indicator variable. It's just 0 and 1. So you take the Hadamard product with respect to the weights. So the C is like the Cartesian product of 0, 1 over like all the weights. So you have one C, like one weight of C associated to every weight or every connections like in the network. So for MNIST, like it's a 786 by 300 2D like weight matrix. So you have a similar number of C matrix that has the same dimensions. So the C is like a matrix of 0 and 1, like theoretically, but they change it to a matrix with values that ranges from 0 and 1.
So if the values of C are 0 and 1, it's not differentiable, right?
Yeah.
So how they're gonna backpropagate the gradient on that?
Well, they do that like by relaxing the constraint. Instead of like exactly 0 and 1, they change it to a range between 0 and 1. So it becomes smooth and differentiable.
Oh yeah.
So they do that with, they call that the indicator function.
Indicator variable, I think.
No. So if you go to equation 7 in the paper, I don't know where it is in the slide.
Okay. Yeah.
No, sorry, equation 7, I think it's in the paper. It's on slide.
I think it's not on the slide.
It's kind of on the slide. It's on, you can see it in slide 10.
Oh yeah, okay.
Number 5.
Yeah.
Step 5, you have CJ equals that weird L. I don't know what that is. They define that as the indicator function.
Yeah,
right.
I think that's a different one. I think
yeah.
that's
So that's what that's partly how they smooth the C value.
Yeah, and I think that's they also like that's just choosing the top K weights So I think S is just the criterion, and SK is like the sparsity value. It can be like point, like whatever. Like if you set the
S squiggle K is the value for the kth
yeah,
element, the kth S value.
the
So
kth largest, I think.
yeah, that's exactly it. So that is your marker. That's, you know, anything above keep,
That's
anything
the threshold.
below.
Yeah.
Correct me if I'm wrong, but doesn't that isn't that a 1? And doesn't that basically mean that this is a matrix of 1 subject to this condition within the brackets?
They define it. So if you go to the paper and you go to equation 7, they define it as the indicator function. So
I've seen this notation used in the context of masks. That's the reason.
I mean, it could be.
Yeah, it's just
It could be.
It is not differentiable, the indicator function, right? If it's above threshold, it's
yeah.
or it's 1. If it's below, it's 0.
I can explain, like, this indicator function is different from the one that are on C's. That's what I was trying to get to. This indicator function, this is an indicator function. So like this is what this means is like it is 1 when the condition inside the brackets are true, and it's 0 otherwise.
Yeah,
So,
that's what I was saying.
Yeah. So this is yeah.
But that's not differentiable.
No.
What could be differentiable, however, is essentially a ReLU. You know, so it's keeping these S values, you know, Sj minus the kth element. Anything that's negative is below the kth element, right? And so if you ReLU that, you're turning everything that you don't want to keep to 0, and everything else is keeping its gradient. That's how I perceived it. But they don't say anything, they don't detail the indicator function.
Well, ReLUs aren't differentiable either. They're sub-differentiable, right? So maybe they're just
sub-differentiable.
Yeah.
just
I mean, we do it. We do it. So. But I don't know. It wasn't clear to me. It could be a binary mask. I'm not sure.
I mean, it looks like that to me because you see a bunch of element-wise multiplies by C after this, which if 0 and 1 element-wise multiplication is a mask.
Right, and that would make sense in terms of you only use the weights. Basically, you're basically masking the weights for the loss function, right? And that is the update for the new weights. In that sense, it does make sense.
Yeah.
But the optimizing through it is unclear, or computing optimization.
I think I got a totally different idea about how this math worked. Maybe I'm wrong, but I think this one, like the CJ, it just like this is after the optimization to choose the top K parameters. It just simply says that if we have a threshold of point, like something, like if it's 90, we want 90% sparsity, then we are just like, after we are done optimizing, because after we are done optimizing, we just choose the top 10% of the weights that corresponds to the top 10% of the gradients by magnitude, and we just select those. I think this is.
I think you're right. So the trick is this little g is the loss gradient with respect to C. It's unclear how they compute it.
Yeah, I think they compute that by like formulating this. So this is just the gradient of the Hadamard product of this one. Passing a mini batch of data. So this is different from that indicator function. That's what I was trying to get at.
Yeah. I think it is different. It's just like, so they do like a Taylor expansion at C equals 1 or something like that.
Yeah. So what they do is like you take the Hadamard product of the indicator variables with the weights and indicator variables, and you change one weight. So like delta times like the standard basis. So
okay. So it's
yeah,
ReLU.
yeah.
It
Yeah,
is just a linear change around
yeah. Like you
around.
change delta amount, like you perturb with a.
There is no functional form assumed or anything. It is just like, yeah, infinitesimal perturbation around one.
Yeah.
Why not
Yeah.
around 0? But okay.
Yeah, that's true. Why not around 0? But yeah, I guess it should work around 0 as well, right? I don't know. Maybe it would be the same.
I don't know.
Anyway, so you pass a mini batch, like PyTorch can calculate it with AutoGrad, like all these derivatives at once. So you get the gradient of the final loss function with respect to each of the indicator variables corresponding to each of the weights, like throughout a matrix of gradients, and you just choose the highest gradients as the most salient weights. So that's their whole algorithm. So it's like kind of straightforward. So their algorithm is very susceptible to initialization. Noah was also explaining that to me today. So it has to be a variance scaling initialization. So then you take like one mini batch of data, you pass that through their objective function and the network, and in return you get this SJ, like the highest gradient, and you choose the top some percentage of the gradient, the percentage of the non-zero weights that you want to keep, and then you fix those and train the network. So you get a sparse network right at the initialization, because you only need one mini batch of data to select the weights. In general, like in other pruning algorithms, you need to, for regularization based algorithm, you have to go through the whole training cycle to select to get a sparse network. But here you can just take one mini batch, make one forward pass, and that's it. You find out the important weights.
So the sorting is just for taking the highest K, right?
Yeah. It's just to select the top SK, the parameters.
Yeah.
It might be wrong SK, yeah, but the top percentage of the parameters. So as an experiment, they visualized like the weights that they found out using these criterions. So these are the first layer for MNIST and fashion MNIST. These are the first layer indicator variables corresponding to the first layer weights, and they reshaped it to the images. So you can see like the brighter it is, the more salient it is. So this starts from 10%. So like at 90% sparsity, their criterion absolutely found out the shape of the numbers. So at the start of the training process, and also in the fashion MNIST, they kind of found out the shapes of the figures. So this and like as I said, their algorithm is dependent on the data. So they also experimented with the number of batches. So passing one instead of they passed one mini batch with only 8s. So with that, the first layer weights that they that survived are exactly at the shape of 8, but with more variations in the training shape, it just converges to the average of all the samples with increasing the size of the mini batch.
Can you explain this figure more as like
This one?
the one on the slides? What is that? Because okay, number 8 on the left is the data, an input sample.
Yeah.
How it is connected to the weights? What is the weight? What is a weight in this picture? Is it a CNN network?
This is the feed-forward network. So this image is just the first layer weights. The weights of the first layer.
One
Net, right?
neuron.
Yeah. One neuron that is connected to the input.
I still don't understand. So what are we seeing? So first layer has whatever height by width weights for each neuron in the second layer, right? Each neuron in the second layer has n squared weights. So we take that neuron and we plot it layer by layer, and suddenly we see number 8. Oh yeah, we initialized it randomly, but we got number 8. That's amazing. I mean, this is a very good result. How did they manage to do that? When you initialize those weights, I just don't follow. What are we seeing?
It's after it's not random initialization. It's the first layer weights after a single pass of the data.
But the weights don't change, right? The weights are randomly initialized.
These are not the weights. These are like the indicator function, indicator variables corresponding to the weights. So they are just selecting the weights that they have survived. So like in the first layer, there are 786 pixels for the MNIST. So there are 786 weights in the first layer, first neuron, one of the neurons. So after their passing of the mini batch, the weights that survived
for this one neuron.
For this one neuron, the weights that survived are like these weights. So these are not the magnitude or the values of the weights. These are just the weights corresponding to the indicator variables that survived the pruning.
Okay, I get it. Thank you.
Yeah. So
like this is like the C matrix.
Yeah, this is the C matrix. So if you pass one sample, so what we did,
it's the C part of the C matrix that corresponds to this one particular neuron in the second layer.
Yeah, exactly. Yeah. So
I bet for for one sample, they're all the same. They will be all the same.
Yeah. So they pass one sample in the mini batch, then they pass 10 samples in the mini batch, then like that's so they increase the samples so they pass one mini batch, so they vary the samples in that mini batch. So the larger the samples in that mini batch, the more the weights that survive converges to the average of the pictures that are on that sample. So that's how they're saying is that their criterion like extracts the weights that are only necessary and removes the background that is not important for the classification.
Do they show how this look for for the batch size larger than 1? Do they show how other neurons look? Are they all the same?
It's just one. I don't think they have it in the appendix. Yeah, just one neuron.
Go ahead.
Okay, so so that was the effect of the data. depending on how many data we have in a mini batch and how that changes the neurons. And there is like also an effect of initialization. So basically, like their method is very susceptible to initializations, and because like the initial weights have a fixed variance, and the signal passing through each layer does not guarantee to have the same variance in other layers. So this would also like make the gradient to be dependent on the architectural characteristics. And so Snape like proposes to use the variance scaling methods for initialization. And for smaller networks like the LeNet 300 or like the feed-forward network, the initializations really didn't matter much, but for larger networks, variance scaling performed well. I think maybe if Noah has anything to add here.
Yeah. So they talked a little bit about like the effect that, you know, the random initial state has on it, but Eloy even mentioned this, like your first random state can be incredibly impactful on your model, you know, to the point where random initial states can actually be close-ish to being a solved function. They tackle it by doing just variance scaling. So at each layer, they scale the variance to be some value. They just cite a LeCun paper, and I didn't read it, so I don't know how they do it, but it's, yeah, I'm sure it's some super simple thing. But I wonder if there's more that they could be doing to correct for the randomness of the initial state. And one thing, and this might be obvious, but I was curious as to why they didn't initialize the whole model to be 1. Calculate the loss, prune using their same method, and then reinitialize the values that they did not prune. Because it essentially turns it into like a min cut max flow problem, where you're looking at, you know, what is the most effective path and equalizing each path from the input to the output.
Yeah, I was also thinking, looking at this, I'm thinking, can we use this, those ideas for better initialization instead? Not for pruning, but for better initialization. And so what you're suggesting would kind of be going along that way. Sounds like something quick to try and see if it will give you better initialization that converges quicker.
It would be incredibly quick to write that up.
So if anyone wants to volunteer and try that.
So moving on, fitting random labels. So one last experiment they did was to fit random labels. What they mean by that is they shuffle up the labels in their data set after pruning. This is after pruning. So this is to test the like whether the model is generalizing or whether it's just memorizing or doing any sort of that stuff. So there is this paper. I don't think I mentioned it here, but let me pull that up. So it's by Zhang et al. 2017. That's on understanding the generalization capabilities of deep learning models. So they introduced this experiment, if I'm not wrong. So what they did was like to shuffle up the labels and really randomly shuffle up the labels. So that would destroy all sort of like correlation with like the structure of the image and with the labels. So, but like large models still manage to like learn and converge even in that setting, because like there's just way too many parameters. But what SNP did was like they showed that without their pruning, the model could still converge on random labels. So that means that it was kind of memorizing whatever connections it had with the images and the labels. But after their pruning, it was not able to
Interpretation.
yeah, it was not able to like learn the random labels, but it was able to like properly learn correct labels when the labels were in the like
Yeah, but that
correlated with the images.
disagree with interpretation of memorizing.
Yeah.
It's just yeah, memorizing. Maybe they mean that the model is not flexible anymore, but yeah,
Yeah.
we're feeding
Yeah.
flexible universal function approximator when we don't have the pruned model. It's a universal function approximator, so it can approximate any function, random or not. It doesn't know anything about the label placement. So there.
Yeah, they were not very like strong about this one as well. They're like it supposedly maybe means that.
Yeah, but
we're not
it's
gonna-
interesting to think about it because why the orange line is flat, why the loss doesn't go down? Because, okay, well, first of all, did they have every label in their batch? Do they require presence of every label in the batch? Or what kind of a requirements on the first batch that they use for pruning? What if I put all number eights there, just digit eights? Will it still work like that, or it will not even learn at all? Like that's what they're indicating, that it's label specific, but I don't think so. I think it's just the model is too weak or something like that.
Yeah, that may happen as well.
They're
Yeah.
getting a weaker model, which is fine as long as it performs good on the class. But yeah, very interesting observation.
Yeah, like in the actual paper they borrowed this experiment from. So in that paper they also like did experiments with large models with randomly shuffling even the pixels of the image, but the model was still able to converge. Like it was just Gaussian noise, I guess, but still like the model was able to converge. So yeah, with that, that's the end of the presentation. I guess if anyone has any questions.
Well, I can thank you for the talk, and thanks Noah for some interruptions, but not enough, you know.
Yeah, I guess I blazed through the first part. Sorry about that. But yeah.
Well, you like the good thing about those talks is like I'm coming to it. I don't know what you're doing. I don't know what is.
Yeah.
Well,
I guess.
I'm sort of no, but it's like you can't assume that everyone read the same things,
Yeah.
and if they did, they can remember them. So it's
Yeah, that makes sense.
very helpful to get like look at the geometric deep learning by Michael Bronstein. The talk. It's all about background, nothing actually about the detail.
Yeah, I should
Different
spend
talk. Yeah.
more time
But this is
anchoring the problem.
I think it's kind of surprising that in one shot before training, you can actually prune a model. Yes, we knew what Eloy was pointing out, that we have like a ball with like the flat part of the ball of the error function is so large that we can even randomly get there and be close to the good performance. But here it's like you can prune in advance.
To me, it looks like sort of an extreme version of inductive bias, where you're just saying like, we first have like the convolutional inductive bias, but then we're going even further and we're removing all of like it's like saying you need vision only in this tiny, tiny space of your eyes, right? It's basically like a sort of like an extreme inductive bias, saying like, oh, we're gonna inductive bias based on the data set, not even because you're doing a mini batch, so you're doing it based on the sort of like the data set you're using.
Well, we only have minutes, but I have strong disagreement with.
Again, I mean, it's not an inductive bias, but like, I mean, I guess
understand what you're saying. I understand what
In
you're saying.
this case, you're basically saying like only look at this part of the image. So you're saying like we don't need all the rest of the vision. We only need to look at this tiny spot because that's the only thing you see in the average of the data set, right? Like,
But I mean,
No,
to me,
I disagree with that. It's not that you're only looking at a part of the image. Your function, your model is huge. There's a ton of redundancies. There's, however many millions of paths from one input feature to the output. And what you're doing is you're removing those paths.
No. I get that. But like, I know about like, I know, but like in this case, they focus a lot on how like the first, second layer. I mean, this is the thing, right? If there's no path from the input pixels to the first layer, which is what they show, there's no pixel, no weight further on in the network, no neuron can ever see beyond like this sort of 8 figure that you have in the beginning. Doesn't matter how complex you make it. If the first neuron does not get that input, you can never get it in the rest of the network either.
Well, but there is usually a holistic neuron. When you run NMF, when you run ICA, one of the neurons is the background. So they don't show us anything. They just, I mean, it's kind of like, oh, look at this neuron. But there is usually a background neuron. So we don't know. What you're saying, we don't know. Maybe after the pruning,
Right, okay.
we still have a full basis. We don't know.
It looks like they're just masking out a lot of neurons also in the first layer. I know they're also pruning stuff like in later layers, but it looks like they're also pruning a lot away in the first layer. And that kind of, to me, it's like kind of like, you're looking, I mean, this is specific to MNIST, right? Because if you would do this on like another data set, you would not get the same result, right? Because MNIST just has like a large background that you can basically say, well, we're going to prune this away because it doesn't matter anyway, right?
I think they did it on Fashion MNIST, and also I don't know if they did in Cypher. I don't think they did in Cypher. Just let me check. Yeah.
This does look like the Fashion MNIST. It does look like if they put one mini batch of only shirts, that's what it looks like in this case.
Yeah, but they
Well,
also did that with
singular.
Cypher 10 as well. So I mean, it works in Cypher 10 as well. So Cypher 10 is like images.
Oh, but you need a different network, different initialization, different data. Like what I'm reading you, Eloy, is like if you initialize on MNIST, it's not going to work on Fashion MNIST.
Yeah, that's what I mean. It's like sort of you're increasing. To me, it also kind of feels like you're very focusing on like a single data set, which to me, I mean, it's not specifically inductive bias, but it sounds kind of like you're basically fitting your network before it's starting training purely on this data set. I mean, if you do like a very big like NAS, like a neural architecture search, you can maybe also find a network with like the same types of parameters. Like that's what I'm trying to say.
Well,
like
but that's the trick.
But
Search, very big are the keywords, and this is just in a snap.
No, true, but like, yeah.
But you can do that with any data set, right, Eloy? I mean,
true, but that's what I mean is like it sounds. I agree with everything you guys are saying. I'm just saying like it sounds kind of like an inductive bias purely for finding Fashion MNIST things, because that's basically what you're doing, right? You're just saying like, oh, we only want pathways that go for shirts, pants, whatever is in the data set.
Well, we're almost out of time. Let me finish with a piece of folklore. Like we know that if we take large sparse model and train it from scratch, it will perform better than a model with the same number of parameters that are compactly organized. So it's not just about, I think still, it's not just about the field of vision. It is about, you need that structure, but you don't need all of the elements in that structure.
No. Yeah, I agree with that. Although you do have like,
how it works.
You do have like weight agnostic networks and like architecture agnostic networks that just it doesn't even matter what architecture you have, like it'll learn the same thing. So that's kind of what I'm getting at too. I mean, I did an internship at a company where we could literally just prune away 90% of the weights, make it all quantized, make it fit in like 5 megabytes instead of like a gigabyte of the network. It used to be like 500 megabytes, and you prune it down to 5 megabytes, and we had the same performance. but like, so I know it's not about like like purely, I get what you're saying. It feels like you're, convolutional layers. Like the thing is with transformers, you have even more weights and you can get a little better performance, that there's almost no inductive bias in transformers. Then you go to convolutional neural networks. And this is just one step further. You have a network and you prune away weights before. That's why, to me, it feels kind of like an inductive bias in a way.
Eloy, we're out of time.
Sorry.
So sorry, I just have a last question. So
Okay, go ahead.
oh yeah, so does it pruning thing, Riyasat, just help in the training process? I mean, like reducing the time we need to train the model, or does it also work as a regularizer to boost the accuracies a little bit?
I think I and Sergey was like discussing this before our workshop paper, whether, I mean, it should.
Yeah, I mean, it seems like the indicator
benefit.
functions are removing some weights, which is kind of dropping out weights, right? So it kind of helps
So-
generalizing the thing, right? Reducing the overfitting, kind of.
I mean,
Well, it does remove overfitting, the random labels plot. It doesn't learn random labels, so that's good.
right.
But Eloy, you're a hard person to convince. Are you gonna be like? I hope you join the next week, Friday, because Noah will try to convince us that whole-field networks is all we need, and we need you there, Eloy, to object.
I will not be convincing